Hi, welcome back to Statistics 1. We're up to Lecture 7 now, and we're ready to jump into regression. And today we'll just do simple regression, and then in Lecture 8 we'll do multiple regression, and then in Lecture 9 we'll see both simple and multiple regression in action in R. So these next 3 lectures tie together, and a lot of the concepts I introduced today will be important not only for today's lecture, but for lectures 8 and 9 as well. So today is a very simple, basic approach just to give you the general concepts in regression. And today's lecture is just 2 segments. We'll do one segment that's the bare bones basic introduction to regression. And then in the second segment, we'll go back and talk about null hypothesis significance testing again. And again, that's a mouthful, so I prefer to just say NHST. We talked about NHST when we talked about measurement issues and correlation. If you remember, we talked about validity and reliability and using NHST as a way to get at reliability of correlations. It turns out there's a lot more we need to discuss in terms of NHST. There are a lot of problems with that approach, and many people don't like it. We'll talk about those problems, and we'll talk about some remedies or some alternatives to NHST. So let's dive into the first segment. This is Introduction to Regression. The important topics in this first segment is just to understand what the regression equation is, and likewise what the model is. So you'll see that the regression model is really just the equation. Then we'll talk about the idea of estimation of regression coefficients. That's ordinary least squares is the approach we'll take at first. And then it's important to understand at the outset the difference between an unstandardized regression coefficient and a standardized regression coefficient. So first, let's talk about just what regression is, generally speaking. It's a statistical analysis used to predict an outcome variable from one or more predictor variables. So you might think, well, this is just like what we did in correlation. Well, it's more complex than correlation. So in correlation, we simply had 2 variables, x and y. Now we're going to have still just one y variable, and that's the outcome variable. But now we could have a whole set of predictor variables. So we could have multiple x's, and we'll predict the outcome variable on the basis of multiple predictors. So to go back to the baseball example, in correlation, we could predict how many runs a baseball player would score, that was our y variable, based on their batting average. The first thing to understand is the regression equation and the different components of the regression equation. And first, let me just be clear about terminology. In this segment and in this part of the course, I'll typically refer to y as the outcome variable and x as a predictor variable. When we're talking about experimental designs, and when we get into t-tests and ANOVA later in the course, I'll typically refer to y as the dependent variable, and I'll refer to x as the independent variable. So you can think of this in those terms, but remember, go back to lecture 1 where we made the distinction between randomized controlled experiments and observational studies. Here, I'm mostly just assuming still observational studies. We're just dealing with correlations, predicting outcomes on the basis of correlations. So I prefer to use the terms outcome variable and predictor variable. I'll save this terminology for true experimental designs. So again, by way of just clearing up terminology and confusion over notation, again, as I said, I've taught this material many, many times, and students get confused sometimes over notation. So you may see the regression equation presented if you just Google regression, if you go to Wikipedia, look up regression. You may see just the formula for a line, which is y equals m plus bx. where m is the intercept, b is the slope, you might see a slightly different notation. Y equals a plus bx plus e, some error. The notation I prefer is actually this third row, or third line in the slide. That's y equals b sub 0 plus b sub 1, x sub 1 plus error. This is what's most standard in statistics. So b sub 0, again, is just the intercept for the slope of the line. B sub 1 is the slope relating x to y. And e is our prediction error or residual. So if I write this out as the predicted score on y, then I'll write y with a little hat over it. That's the predicted score on y. Is that same thing, just leaving out the error term. So of course, the difference between the actual score y, or observed score y, and the predicted score y is error. I'll call that prediction error or residual. So if we go back to one of our examples, this was predicting number of runs scored from batting average. We saw a nice correlation, positive correlation of 0.4. What I've done now with this plot is I put the actual player names next to each individual dot. So you see for that one dot up here, that's Curtis Granderson, player for the New York Yankees. He actually went to UIC, where I used to teach. I think he actually took my stats course. You see a big prediction error for Curtis Granderson. Same for Eduardo Nunez down here, big prediction error. For the rest of them, not so big. Okay? Those are the residuals for those individual points. That regression, or that regression equation, we could run it in R and get the regression equation. We'll do that in lecture 9. That's the model. That's what I mean when I say model. The regression equation is just the model. You'll see that our models will get more complex. We'll have multiple predictors. So the models will be more than just this one equation, but for now it's just this equation. And the whole point of this is to build better models. So I like this title, Regression, it gets better, because the goal is to produce better models, to come up with better predictors or more predictors that will explain more of the variance in our outcome. So we did that with this example. We instead of putting in batting average, we put in on base percentage. We just came up with a better predictor. But we could do other things. We could try and come up with more reliable predictors, or just add in more predictors to the model. So we did that, and we got a better model with a correlation of 0.72. And let's look at those two players that I looked at before. Granderson's now up here. Still a pretty big prediction error, but not as bad. Nunez is way down here. Very small prediction error now. Okay, why did they get better? So on-base percentage, you can think of that as a model. It takes into account walks, or base on balls. And the model did particularly better for two players, Granderson and Nunez. And if you look up their statistics, you see that Granderson walked a lot. So Granderson got on base a lot, allowing for him to score more runs. So when we took into account walks, or base on balls, which on-base percentage does, then the model did much better, particularly for Granderson, and particularly for Nunez. Nunez didn't walk very much at all. He didn't get on base very much. So when we took that into account, the model did better. So one fundamental lesson to take away from that simple example is look at your residuals. Look at your prediction errors. What is your model getting wrong? If you can start to spot patterns in your residuals, then you can start to think about how you can improve your predictors, or you can think of other predictors to add to the regression equation. And the way we're going to do that, and you'll see this in lecture 9 specifically when we do regression in R, we'll plot residuals in a histogram. So you can imagine if I plotted those residuals in a histogram, remember a histogram, if we have a normal distribution, it just looks like that, right? If we plotted residuals, we would want to get most of the residuals around 0. Right? Some of them are going to be positive, some of them are going to be negative, but they're going to be small. They should be near 0. What we saw in that case is we had a really big positive residual for Granderson, that one player. So that made us think, well, why for that one player do we have this one extreme score? So if we just looked at the histogram of residuals, we would see the extreme scores, just like we saw way back in descriptive statistics. Another thing we can do is think back to the correlation chapter or lecture. We could plot a scatter plot where we look at x and the residuals. And here we shouldn't see a relationship between x and the residuals. There should just be sort of all over the place. There shouldn't be a function relating those two. If we did see a relationship, that would suggest something like heteroskedasticity. If you remember from the correlation examples, let's say, for example, we had a scatter plot where there was no relationship at the beginning, but then a relationship at the high end of x, doing a scatter plot between x and y. Then if I looked at the residuals, then at the bottom of the distribution here, I would see big residuals. And if I looked at the top of the distribution, I would see small residuals. If the residuals are a function of x, so if I did a scatter plot looking at x versus the residuals, and I started to see a relationship, then I would know that I would need to add in another predictor, or that my x score was biased or in some way, or had a confound. So that, again, is a way to test these assumptions of correlation and regression. One, that we have a linear relationship between x and y, and two, that we have homoskedasticity. I'll get into that in more detail in the next lecture on multiple regression, and then again as we do this in R. So how are the coefficients estimated? Here's our regression equation. We have the intercept and the slope. How does R, or how, if we wanted to calculate this by hand, how do we come up with those estimates? This is where the concept of ordinary least squares regression comes in. And the idea is very simple. We want to minimize the residuals. We want to minimize our prediction errors. So the way to do that is just like we did descriptive statistics, where we calculated sums of squares, we can calculate the sum of squared residuals. Because again, some of the prediction errors we're going to predict too high, so they're going to be positive, but then others we're going to predict too low, they're going to be negative. So if we add them all up, they're going to sum to 0, just like the sum of deviation scores. So we'll square them, and that'll give us the sum of squared residuals. And what this process, ordinary least squares, does is it minimizes that value, sum of squared residuals. So we can think of this in terms of a Venn diagram. If we look at this circle here and think of that as representing all the variance that's in our outcome measure y. So baseball players score different amounts of runs over the course of the season. There's variability in that. If we looked at the histogram, we'd have nice variability. Let's represent that in terms of a Venn diagram. So we have all the variance in y. Then we have some predictor variable x, batting average or on-base percentage. And if x and y overlap, if they co-vary, remember from the lecture on correlation, then that represents the covariance or correlation. And remember, we calculated that by calculating sum of cross products for x and y. So that's represented in this shaded region here is the sum of cross products. Contributes to the correlation, to covariance, and will contribute to the slope of the regression line. We can also refer to that as sums of squares for the model. When we have more than one predictor especially, we're going to call that sums of squares for the model. So if I look at my outcome measure y, I can sort of parse the variance into two pieces. Sums of squares for the model and sums of squares residual. That is, variance explained and variance that's not explained. Basic way of categorizing or dividing up the variance in y. But how would we do this if we just want to do it by hand? Well, for simple regression, which is what we're doing right now, just one predictor variable, one outcome variable, it's really easy. For multiple regression, which we'll do in the next lecture, it's a little more difficult and we'll have to do a little matrix algebra. It's not too hard. We'll cover it in the next lecture. For now, simple regression, it's real easy. All I need to know is the correlation coefficient, and we went through how to calculate that. Remember, that was just calculating sum of cross products relative to sum of squares in x and y. So that's little r, right, correlation coefficient. And then we multiply that by the standard deviation for y over the standard deviation of x. And that's how we get the unstandardized regression coefficient, which is just the slope the slope relating x to y. So just go back to sort of high school geometry, right? The slope of a linear function is just rise over run. Remember that? So for a 1 unit increase in x, it's the predicted change in y. Right? It's just rise over run. And if we want to do this just by hand, we could do it with this simple formula. It gets even easier if we want to look at the standardized regression coefficient. So if you look at the standardized regression coefficient in simple regression with just one predictor, I'll refer to that as beta. And that's a common notation across statistics, is to use the notation beta for the standardized regression coefficient. If we just have one predictor, then beta will equal r. It will be the same as the correlation coefficient. And if you look back to this formula I just gave you, if we're dealing in standardized units, z-score distributions, again, go back to descriptive statistics, then the standard deviation for y is 1. The standard deviation for x is 1. So 1 over 1 is 1. Multiply that by r, then you just get r. That's why the standardized regression coefficient is so easy. It's the same as the correlation coefficient. So again, we wind up with just beta equals r. That's only true in simple regression. In lecture 8, you'll see in multiple regression, it gets a little more difficult than that. So again, let's go back to this example. If I run this in R, and you'll see in lecture 9 that the function we'll use is just LM in R. That stands for linear model. It's just LM, open parentheses, y tilde x. So LM, outcome variable, tilde, predictor variable. Here's the regression equation from R. It looks a little weird, doesn't it? Negative 282 plus 1044 times x. Why is that so weird? I'll get to that in a second. If we wanted to get predicted scores on y, then we just plug in values for x. So let's say a player had non-base percentage of 0.350. If I plug that into this formula, 0.35 times 1044 minus 282, I'd get a predicted score of 83. If you go back at the scatter plot, you'd see that's about right. So you get 0.35, here's 0.35. If I go up to the regression line and then over to y, I went a little high, but you get about 83. Okay? And you can do that for any value of x, plug it into the regression equation, get a predicted score on y. But again, why are these values so weird? We have beta sub 0, the intercept is negative 282. Writing's a little sloppy there. And beta sub 1, the unstandardized regression coefficient, is 1044. These numbers are a little hard to interpret. Why is that? First, before I advance the slide, let me deal with the regression constant. Why is this negative 282? Well, the intercept is the predicted score on y when x is 0. If we go back and look at the scatter plot, 0 isn't even on the y-axis, right? This would be what would we predict if somebody had a 0 on base percentage? Well, that didn't happen for any of these players. So that's why we have such an odd predicted score. We would predict that they would score negative 282 runs because that didn't happen. The other odd thing about this, and sort of difficult to wrap your head around, is why are these numbers so large? No one scored 1,000 runs, right? If you look at the scatter plot again, the range is 40 to 140. Why do we have a scatter plot? Why do we have a regression coefficient of 1,000? Well, it's because the scale of y and the scale of x are so different. So if you look at the scale of y, it's in runs. It was like 40 to 140 was the range. If you look at the scale of x, it's a percentage or a proportion. And it was from 0 to 1 is the highest you could possibly get, but our actual values were about 0.3 to 0.4. Remember, what the regression coefficient stands for is for every 1 unit increase in x, it's the predicted change in y. Well, a 1 unit increase in x is a big jump across this scale. So that's why the predicted change in y is 1,000. So if we just move the decimal point over, say we move it over 2 places, then we'd get, instead of, actually just move it over 1 place, then we would get a predicted score. If we go from like 0.3 to 0.4, then we would get a predicted change of about 100 runs. And that's what you see. If you go from like 0.3 to 0.4, then you'd go from about 40 to 140. So the point of all this, and to explain why we have these numbers that are a little hard to interpret, is because they're unstandardized. And the scale for x and y were so different. That's why we often rely on the standardized coefficient to interpret the magnitude of the relationship between x and y, because it's just simpler to interpret. So to wrap up this segment, the most important things to take away are, what is the regression equation? It's just, at this point, in simple regression, It's just the equation for a line. We have intercept and slope, x and y. We're still assuming that x and y are both continuous, both normal, and there's a linear association between them. We'll move beyond those assumptions later in the course. Understand what ordinary least squares estimation does. We'll come back to that again in multiple regression and in lecture 9 in R. And then the importance of this distinction between unstandardized and standardized regression coefficients.